see us waking up. So I'm just waiting what they do, and we start. And of course, we're very happy to present you the 8 teams which were certified for Nanocar Race. Okay, hi everybody. I'm very happy, since I'm from Toulouse, I speak a bit in French for 5 seconds. Merci beaucoup d'être tous présents pour assister à la présentation des 8 équipes qui ont été sélectionnées pour participer à la course de voiture 2022, qui sera en mars 2022. So now I shift in English for all the other people which are waking up in Japan. It's about 2 or 3 o'clock in Japan. Chicago, Houston, they are more at the breakfast or lunchtime soon. A bit in California. And of course, for all Europeans, they will be happy for all Europeans to listen to us. And so the first thing, thanks to the nice talk by Francesca, Francesca just introduced you how to rotate a molecule, just tell you how you drive a molecule, and just take one example from the past race, which is very simple here. You see here just a tip, bringing some energy to the molecule. Let's select the Japanese one because Japan cannot be here today. And you see on the right the molecule also, which is moving. So this molecule can continue to move, and you can learn like this to drive along a surface. So this was Nanocar Race 1. For those who forgot what was Nanocar Race 1, maybe you forgot, it was 28-29 of April 2017, 9 teams registered, 6 teams were certified, 4 on the same surface, 2 remote control, 2 winners, Graz, here present, Graz, where are you? Ah, here, good. And Basel, which are not here because they don't candidate this time. So this was Nanocar Race 1. In 2018, for MEMO European project, we decided to organize Nanocar Race 2. Thanks to COVID, we were obliged to shift to 2001 to 2002. And we have a lot of troubles with that. We launched a call all over the world, and we received 23 answer file, official file with molecule design, team, chemists, physicists, theorists, STM, blah, blah, blah. They are all here. Fortunately or unfortunately, you see, they are all based on the north part of the world, if you put the world on the good side. And at the end of the selection of certifying process, 8 teams remain. Some are joined together, and I'm very happy. Tonight, we have 7 teams represented here for you, and they will all describe 6 minutes sharp, each of them, allowed 6 minutes, their team. I don't give them any format, so we have a different type of format of their presentation. And the first one will be soon. And first of all, I like to thank a lot of persons which help us to organize number 2. All the bureaux du CNRS à l'étranger, which are the people representing CNRS all over the world, USA, Japan, China. After that, the French embassies and consulate all over the world, which help us to disentangle some proposals which are not so clear. The scientific attaché of USA, Japan, Germany, Austria, and Spain, plus Institut Français on 2 countries, Saint Sebastian and also Vienna. Special expert, we need sometimes some expert per country to help us to speak Japanese, for example, to a team. So there was also China with Emingo, Jean-Pierre Launay, a special specialized, and Germany. And also we have a national committee representing all the continent and a special mentor, which is Jean-Pierre Sauvage. So all of these people help us to organize Car Race number 2 and to select the people. And I want to mention also all our sponsors and support, which are all here. You can distinguish one. I will just mention 2 of them because they decide to give for the winner, maybe one of those which are here. They will have 2 prizes. Nature Nanotechnology offer 1 year's paper of the issue for 1 year, guys. And Springer, you will get a series of books. So this is the 2 first prize offered by a sponsor for the winner of Nanocar Race 2. Well, guys, you have to. So now the A certified teams, they will go one by one. And I call first the first team, which is the Dresden team. Dr. Liesel, the floor is yours. You just have to push pop-up. 6 minutes, and the microphone is there.
Okay, great.
No problem.
Thank you, Christian, and hello. I'm happy to welcome all of you today. My name is Francesca and I'm very happy to present to you.
It's okay. Go ahead. No problem.
I'm very happy to present to you today our team, the Team GAZE, the team from Germany, German Azolene Explorer. The Team GAZE is based in Dresden. We're a very multidisciplinary team, as is required. So we have, from my side, my group are organic and polymer chemists. So we are the one who are building the car. We are a bit like the engineers putting the wheels on. We have the group of Francesca MORESCO physicists who are driving the car, so they're of course like central to everything. And then we also have the group of Dimitri, who is calculating everything, a theoretician who's helping us to understand what's going on, in fact, on the surface. So as I said, like my team or my group, you can see here, Functional Electronic Materials. We're based at the Leibniz Institute for Polymer Research. So we're synthesizing organic molecules and polymers. And we are focused on the synthesis of functional electronic materials. I would like to point all of you to the young lady who is on the front, like to the right. This is Umayma Aboudi. She's a PhD student in my group. She's a NanoNet scholar, so she has a stipend from the Helmholtz Association. And she's originally from Morocco, from Casablanca. And she's the one who's like doing, like, let's say, all of the hardcore work. So she's synthesizing all molecules that are being investigated as nanocars. Then we have the single molecules machines group, which is, like, let's say, centered around Francesca MORESCO. You saw her in the talk right now. So they're located at the Center for Advancing Electronics in Dresden. And they are doing scanning tunneling microscopy and also spectroscopy. So, and the person or the guy in the blue sweater you can see there, this is Tim Kühne. And he is the one who is, or who will be driving the nanocar, with which we will, of course, win the race, I assume. And then you can see here our slightly grumpy, as it has to be, theoretician Dimitri Rudnik, who is doing all calculations and helping us to understand what we're actually doing, because apparently this is rather complicated to design a nanocar and understand what is going on the surface. And now we're coming to the central part, what is, like, let's say, the core of everything that we're doing. What you can see here is the first version of the nanocar that we synthesized. And maybe the name already gives it a bit away, so German Azolene Explorer. And what you can see a bit like in the center of this molecule, you can see two rings, yeah? So one is a 7-membered ring and one is a 5-membered ring. And that is azolene. And most organic molecules do not have a very high dipole moment, yet dipole moment, and this is something you will hear a lot today, is pretty important for what we want to do. And azolene is an organic molecule that already has intrinsically a very high dipole moment, which made it so attractive to us. And now we just like modified it a bit, so we tweaked the structure to give it an even higher dipole moment, and voila, we had like our first version of a nanocar. And what you can see here is that, like, as soon as you bring it on the surface, we either have like single azolenes or they form like some sort of dimer with a gold atom in between them. And what you can also see here is, which is very nice, of course, for us, it's working. Yeah? So they are driving, and you can see a bit of a slalom parkour, which is going on here. So by just like pulsing on with the tip of the STM on our nanocar, the group of Francesca MORESCO is able to move it on the surface. And yes, with this, I'm coming to the end. So I assume I already showed you the winner of the Nanocar race. Here you can see, of course, everybody who is responsible for us to give us a bit of money. I would like to thank all of these. And with this...
Thank you, Francesca. Francesca, thank you. And I have a present for you. If you can stay here. Pierre Abeyot from the CEMES lab. I suppose it's a good one. It's a 3D exact printing respecting the XYZ coordinate of your synthesis. It's a pleasure to offer this one to you. Maybe you will drive, and maybe you will win. Thank you. Whoa. Thank you. The next team selected here. Leo, Professor Grill from Graz University. Your turn, guy.
Hello. Thank you, Christian. Hello, everybody. I want to present you the Graz Race team for this competition, which consists of two partners. On one hand, there are the chemical synthesis people from Rice University in Houston, which is James Tour and Alexis van Wenrooy. On the other hand, there is the team in Graz who is doing the manipulation of the molecules, so the experimental physicists, which is Grant Simpson, Christoph Natschi, and myself, as you can see there. The design of our molecules is based on two assumptions. One is the wheels of the car. The Rice group has tested various wheels to be incorporated into the molecules, and we've decided to use the adamantane at the end, but the different options. And the important thing about the wheels is, on one hand, they should lift up the chassis of the nanocar from the surface to lower the interaction. On the other hand, they should have a lower interaction with the surface by themselves to allow for fast motion and propulsion on the surface. That's one aspect, the wheels. The other aspect is the propulsion itself. And what we have incorporated there, or the chemists have incorporated, is a strong electric dipole moment within the molecule based on this amino and nitro group that you can see there. And that's really key for the propulsion of the molecule, because with this one now, we can move the single nanocar on the surface. We use the STM tip, the tip of a scanning tunneling microscope, that we place in vicinity of the molecule. And now, as we have this dipole moment in the molecule, it wants to follow the tip. So it wants to go to the area on the surface with the highest electric field strength. And that means it jumps, it hops from one side to the next while we place the tip in front of the molecule. And in the end, this means we can move now the nanocar over the surface. In hops, we take an image, we put the tip close to the molecule, another hop, another image, and so on and so forth. And as you can see, the series, we can move the molecule on the surface. But there is a big problem about this. The problem is that we have to take an image after every step. And the slow part of the whole thing is the imaging. Every image takes a minute or a few minutes. And this is rather slow if you have to take hundreds of images on the way. So we thought, can we make it better? Can we be faster by not imaging? In other words, can we do it blind? Can we do it without watching? And this brought us to the idea that we might be able to do that if we find another way to follow the motion. So we can bring truly this molecule you can see at the bottom of the image there to the top of the image without ever looking, without ever taking a single image on the way. And the way we do this is by following the current. This is the electric current that flows through the molecule in every single step. And if we study this in detail, we can tell from the jumps you can see in the current signal, we can tell what the molecule did. Did it a translation or rotation, what happened? And based on these jumps and a lot of experience with these molecules done by Grant Simpson, we can learn what's going on, and we can truly do the whole manipulation blind. So we can do a motion of a single molecule over 190 angstrom without ever looking there. And this brought us the victory in the first Nanocar race. You can see here a movie that should start now, the movie. It doesn't start, I'm sorry. Just to tell you, now this was the parcours, the route to go for the molecule along the Nanocar race, and we could go through there with a single molecule by using the propulsion mechanism I've just shown you. This was pretty efficient. Actually, we were surprised ourselves, and we made it in 1.5 hours, which was very successful. And of course now, for the next Nanocar race that will take place next year, we want to use our experience from the last time in 2017 to build a better nanocar and to make it maybe even faster than last time. Now the team is still the same. It's the Rice University. You can see Jim Tour in the image here and Grant Simpson, that was from the last race. Now we want to have the same team with a different, slightly different molecule, maybe even better. And for that, the chemical synthesis people at Rice, they have designed different versions of molecules. And the important point about the new Nanocar Race is that the molecule must have at least 100 atoms. Our last molecule had 74 atoms, so it was just too small. We have to make the molecule bigger. At the same time, we don't want to lose the advantages of the molecule, which was this very fast motion. So what they did was they've developed a couple of wheels that we could incorporate there. We still want to have a dipole moment, and came up with a number of molecules that have either tert-butyl wheels, as you can see here, or they have adamantane wheels, but now it's larger than last time, or we have a hybrid combination of the two. We use both tert-butyl wheels and adamantane wheels. We have got all these molecules, and if you look on the detailed structure, you will find that they don't have all the right number of atoms. Two of them are just too small, so these two are just not eligible for the race, but the other three are. And now at the moment we are testing these molecules. We have them in our fridge and on the surface, and we're testing them and see what's going on. And with this, we're preparing for the next Nanocar race. Thank you.
Well, thank you very much. Good, good. You have to find your molecule also. Sorry, but yourself, you have to find where is it. This one, fantastic. So you have to. Well, please show your molecule. That's not mine. So thank you very much, Leo. So I cannot say all the team will win. So now, Guy. Henri-Pierre Jacot from Strasbourg.
Thank you, Christian. Thank you, Christian. It's a great pleasure for me to be here to talk about the Stras Nanocar team. Actually, this is a view of Strasbourg downtown, city center. This is a view we have from the campus, so it's a very nice view. But before talking about the science, I just want to quote Richard Feynman, who said, "Consider any machine, for example, an automobile, and ask about the problems of making an infinitesimal machine. I can see no reason why it can be redesigned to work again." And this is what I believe we are all going to try to do during the Nanocar Race II contest. So the University of Strasbourg was founded in the 16th century. What is interesting over there is that we have still a historical campus which was built by the Germans when they took the city in 1870. Of course, we do not run any experiments on this historical campus, so that's why there is a new campus, which is called the Esplanade campus, and this is where I'm currently running my own experiments as a chemist. Concerning the physics, it's done on another campus, which is north side, called Cronenberg, nothing related to the beer, actually. And Strasbourg is very famous for its chemistry, since the university hosts 3 Nobel laureates, Jean-Marie Laine, Jean-Pierre Sauvage, and Martin Karplus. And also there were some very famous professors, such as Louis Pasteur. So our team is a multidisciplinary consortium, as it is for everyone. But actually it's also a very French consortium, because all the laboratories are on the French ground. So I do not work alone. I usually work with Professor Valérie Heitz, who is the PI of the research group I work in. And when we were invited to be part of this Nanocar Race II, we contacted Guillaume Schul, who is our physicist. And we also needed the very special expertise of Dr. Xavier Bouju, who is an expert on calculated STM images. This work cannot be done without the help of young talents, more especially postdocs. And I'm thinking of Dr. Anna Rovslowska, who will be our pilot for the Nanocar Race II, who works with Guillaume. And also Dr. Hassan Denawi, who does calculations with Xavier. Concerning our Nanocar, it's a di-nuclear complex, iridium complex. It has more than 100 atoms, which was required. So the molecule is very small, rigid, and also it has a very important dipole moment on account of the position of the nitrogen atoms around the iridium center, so which is very useful for the manipulation. Then the design is very simple. It has only 2 wheels and 1 axle, and actually it was inspired from my PhD, since I've done my PhD here in Toulouse with Christian and Guénel Rappen. And I was actually the chemist who made the molecule at the bench. Concerning the collaboration, so when we started this project, we wanted to have a long-term collaboration with two main areas of research, one related to molecular mechanics, and the other one related to electrically induced optical phenomenon, and this would need or require additional experiments, more especially on NaCl bilayer. Concerning the physics, the group of Guillaume Schul has two low-temperature STMs, having, of course, the remote control for the Nanocar race. The molecule was already deposited on the gold 111 surface, and you have the corresponding STM image. And thanks to Xavier, we were able to get the geometry of the molecule on the surface, and it seems to be very rigid. So concerning the sponsors, I have to thank the CNRS, the University of Strasbourg, and the Région Grand Est. And I also would like to thank a special thank to the University of Strasbourg, who provided all the nice movies you've seen during this presentation. And oops.
Oh, HP, thank you very much. So we have now to look for your molecule 2. It's fun because there is your one, but also for you, I just offer you your past ones. Like this, you get 2. The big one which never move, and hopefully the new one which normally will move. So you can go here. So, oops, sorry. Okay, so now we have a special communication from the Japan. Mana Nim's team, they cannot make it. We have a representative from Japan, which come in a minute, but now we have to listen to them because they made a video, they are sleeping right now.
Hello, I am Tomo Nakayama, a director of NEMS Nanocar Race team. Today, I introduce our team and strategy for the coming Nanocar Race II in March 2022. This is the NEMS Mana team. 5 members in the upper row are the core members, me, the leader of the team, and Shigeki drives a nanocar with low temperature, ultra high vacuum scanning tunneling microscope. John constructs nanocars through chemical synthesis, and Ayako analyzes the performance of a nanocar using first principles calculations. And Liu provides designs to optimize and customize a nanocar using a machine learning technique. There are also supporting members in our team, like Daniel to help car construction and Masaki to help driving. For the Nanocar Race II, we use a polyethylene-based molecule as a nanocar. This decision is coming from our previous work on a rotation switchable molecular motor published in Nanoletters in 2015. A pair of polyethylene-based molecule is prepared on gold 111 surface, and one of the 2 molecules is pinned to the surface. Then, unpinned free molecule can be driven in this direction, resulting in a rotation of the paired molecule around the pinned position. So if we use only one molecule, the motion of it must be linear. That was our expectation. As you see here, we can actually drive a single molecule linearly on the silver 111 surface. However, we could not achieve satisfactory motion on the gold 111 surface, the racing track of the Nanocar Race II. So John is modifying the first generation nanocar, a monocarboxy platinum molecule, and Shigeki is testing revised nanocars using a scanning tunneling microscope. This is the low temperature, ultra high vacuum scanning tunneling microscope for driving a nanocar. In the course of nanocar development, we are also trying to synthesize a molecule using this instrument. construction of a nanocar on a gold surface is actually possible, and it will make the nanocar race more exciting. The images at lower right shows test manipulation of an on-surface synthesized nanocar. It's moving. So why is it interesting to construct a nanocar on the surface? In the previous nanocar race, we fully prepared the final form of a nanocar and brought it to France. However, by introducing on-surface synthesis, we can simply place components and spare parts on the surface, and then we use those parts to construct a nanocar and repair a nanocar if necessary. As shown here, this mimics the real car race like Formula One Grand Prix, where the pit crews construct and repair the racing cars during the race. Of course, analyzing and designing and customizing nanocars are important for making nanocars better. Therefore, Ayako analyzed the performance Shigeki's driving test using first principle calculations, and Ryo uses such feedback to propose further improvement of the nanocar using machine learning methods. I would like to finish my presentation with a comment on the meaning of Nanocar Race II for us. Is it for fun? My answer is yes and no. Nanocar Race II is not only for fun, indeed. The development of molecular machines will certainly give impact to society in many different ways. And it's not only for race, but also for solving global problems. For example, by actively controlling frictions between the molecule and the substrate, we can manage heat generation. Molecular machines can transport energy and can deliver drugs and can do many things. Anyways, we are very much keen to deeply look into the possibility of molecular machines for our futures. For such possibilities, Toyota is providing sponsorship to our team. Okay, that's it. We are looking forward to driving our nanocar in the race, and thank you for listening. Bye.
Well, thank you, Tomo. You are still sleeping, but thank you very much. And I like very much. Wio is arriving here. So Wio is representing the MANA project in Toulouse. So you find your molecule? Oh, fantastic! You find a molecule. It's there. and now, of course, from Toulouse, Claire Cameraire, Professor University. So I have to push you because this is Toulouse.
Yes.
And to be Japan too. But, okay.
Okay, so thank you very much, Christian. And good afternoon, everybody. So let me introduce our Franco-Japanese team. So in our team, we have scientists from Toulouse, but also scientists from Nara in Japan. And this international collaboration stems from the strong bonds that have been established over the years between the Nara Institute of Science and Technology and the University Paul Sabatier in Toulouse, and also the CEMES CNRS Research Institute. So this collaboration covers the field of education, of course, with a doctoral double degree program, but also the field of research. And this appeared to be the perfect framework, actually, to enter this competition of the second Nanocar race. So our team is composed of 8 members with skills ranging from the molecular design and synthesis, but also calculations and, of course, surface physics. And so 5 chemists were involved in the design and synthesis of our nanocar. Professor Genal Rappen, our team leader, Dr. Kazuma Yasuhara, Dr. Toshio Nishino, Mr. Hiroki Takeuchi, and myself. Dr. Colin Martin, who is a part of our international collaborative lab, was involved in DFT calculation in the gas phase, whereas Dr. Xavier Bouju, here, is in charge of adsorption, DFT calculation, and also image calculation. And last but most importantly, Dr. Olivier Guillermet is the driver of our nanocar. So speaking of our nanocar, for the design, we follow the technomimetic approach, which means that we try to mimic at the molecular scale the shape, but also the function of a macroscopic car. It means that our nanocar is based on a planar chassis, which is surrounded by wheels. In this case, we have only 2 wheels. It's a big, little bit of improvement since last Nanocar race. And as for all the teams involved in the Nanocar race, our aim, of course, is to try to move this molecule without any mechanical contact this time. And also, with the lessons learned from last Nanocar race, we also aim at exploiting the electric field generated by the STM tip to trigger control motion of our nanocar. And so to do so, it's really important, it's crucial to have a dipole moment in the molecular structure, as you have heard many times tonight. So from the chemical point of view, the central chassis will be composed of a porphyrin scaffold, which is flat, it is rigid, and also it accommodates very easily side groups, and particularly the wheels. And very interestingly also, it is able to coordinate different metal ions, and this will bring another functionality to our nanocar, which is a function of cargo, and our nanocar will be able to be loaded with cargo and transport cargo from one place to the other. This will not be useful for the nanocar race, but it's other specific properties. So for the wheel, we selected tryptophan units, so that those are chemical groups that are made of carbon and hydrogen and are 3-dimensional, which is very interesting because it allows us to lift up the chassis from the surface and so decrease interactions. The tryptophan groups have also very good imaging properties, so they show very good contrast on STM images. And as mentioned before, it's crucial to include a dipole moment in the structure of the nanocar, so we inserted a donating group and an accepting group. And by varying the nature of those groups, it's possible to finely tune the dipole moment of the molecule. So here we did not only synthesize one nanocar, actually, but we synthesized a series of 9 nanocars with increasing dipole moment. For this nanocar race, we selected one prototype. It's the one that is squared in blue on the screen, which has cyanophenyl group as an acceptor and diethylbutylphenyl group as a donor. So this prototype was assembled in NICE, starting from very small building blocks that you can see, and it was obtained via multi-step synthesis. So I said this prototype, but I should say these prototypes, but because in fact, with this synthesis, we are able to obtain trillions of molecules. So we obtained here trillions of nanocars, which appear as a blue shiny solid. And this is why our nanocar is called the blue buggy. So after full characterization, we were able to obtain an X-ray crystal structure of the nanocar, and with this, we could access the real dimension of our car, which is 2 nanometer wide and 1.5 nanometer long from the front to the rear. And after all these manufacturing steps, then we could, at last, end a batch of our nanocar to our pilot, Dr. Olivier Guillermet, who was able to successfully deposit the nanocar on the goal racing track, and then by means of scanning, tuning, microscopy at low temperature, he was able to fully characterize the blue buggy at the single molecule scale. And at the moment, we are now training to optimize our control of the motion of this nanocar, and I think we are fully ready for the next nanocar race. Thank you.
You are ready?
Yes.
Whoa. I was not knowing that. So you are ready. Thank you, Claire, very much. So I don't see your molecule is completely overshadowed by you find it.
Yes.
So you find it. Oh, it's gray. Sorry, it's gray. So you can make a stop that maybe you can zoom better for you because you are in Toulouse, so you can make a stop on this one. That's all. Oh, okay. Okay. David. So if this guy wants to go. Okay, now it's Professor Echeda from Madrid, which is introduce also his car. Thank you.
Thank you very much, Christian. So hello, everyone. It's a real pleasure to be here. Thank you very much, Christian, and the organizers for this very nice event, which after the pandemic is really nice to be around and to be really looking forward to March 2022. So I'm here today to show you our initiative, the Swedish-Spanish initiative, which is entitled Nano ISPA Team. So first, I would like to thank all of our sponsors, the European Research Council, the European Commission, of course, and then different ministries in Spain, like the Ministerio de Economía y Competitividad, also Comunidad de Madrid, and especially the Spanish Royal Society of Chemistry and Physics and Sienta Omicron. Okay, I belong to INVEA Nanoscience, and for those of you who don't know us, this is a new institute. In fact, it's the youngest excellence center in Spain. It's devoted to nanoscience and nanotechnology in general. And we have right now over 50 labs and research infrastructures with a growing number of researchers, right now more than 200. And we are very flexible in our lines of research, adapting to new times. Right now we count with 10 lines of research, and 2 of them are focused on surfaces and on chemistry of low-dimensional materials, which are somehow the birth of this project of the Nanocar for our team. So let me show you now the engineers, the real designers of the Nanocar, which is the group from Professor Emilio Pérez, and especially his PhD student, Tomás Nicolás. They are experts in the chemistry and functionalization of low-dimensional materials, and they have a strong focus on the functionalization and study of supramolecular chemistry and molecular machinery in general. Then I go right now to the pilots, which belong to my team. So we have a bunch of pilots, the chief of them, Dr. Kun Laubaet, then it goes Dr. Ana Sánchez Grande, Dr. Ana Barragán, Dr. Nacho Urgel, and myself. And then from Linköping University, that's why we have this Swedish alliance, it comes Jonas Björk, who is an expert, as you know, in the study by DFT of the behavior of molecules on surfaces. Okay, so the start of this project, essentially we were very fascinated from the previous Nanocar race, and we were really studying the papers in detail, and there we took, how to say, the advices. And there it was clear from the winners that we should, if you want to make a good Nanocar and try to win the race, you need to have a very low molecular weight. Also, it should be important that the interaction between the molecule and the substrate should be low. And in principle, of course, you need to deposit the molecules in an easy way without cracking them. And finally, you need a good propulsion mechanism. And to build in a dipole, an electric dipole could be a good mechanism. So taking all these ideas from the previous winners, we decided to propose this molecule, which essentially, the idea of this molecule is to have enough steric hindrance inside the molecule to present a shape on the surface that is going to minimize the interaction between the molecule and the substrate. And also, since we are going to have distinct substituents, distinct moieties within the molecule, we are going to have a dipole on the surface. So in particular, this is the basis of our car. As you see, it's an anthracene chassis, which essentially is functionalized by benzene and by methyl aryl moieties. And the idea here is that those aryls are going to be the wheels and anthracene just the chassis. Okay, here you have the synthesis. I will very briefly comment it. So essentially what we do first is to synthesize the lead, which is a dibenzofuran, and then we are able to couple this dibenzofuran to the precursors of the chassis just by subsequent 4+2 cycloadditions till finally we get the car. Okay, once we have the car, we have tested it, and here I can show you our race headquarters. So essentially, it's a homemade machine hosting a low-temperature STM from Omicron, and we have all the facilities for depositing, inspecting, and manipulating the molecules. And importantly, due to the pandemic, we have a lot of expertise about how to use this machine remotely. Here you can see one of these species. So essentially, after sublimation, we located one of them, and you can clearly see very easily that the shape really corresponds to the molecule. We are now getting the DFT simulations, but in principle, everything is working fine. And here you can see the most important part is that we are able to displace the molecule from an island, from a self-assembled island, and also we are able to distribute the molecule or move along the surface as we wish. Importantly, here we can do this following two mechanisms, as you have seen previously from Professor Leonhard Grill. We can just make a pulse and drag the molecule, attract the molecule and they take an image, or we can also monitor the current, just to go and try to be faster. And now I think I have finished, so I think let's see if we have the animation. So that's what.
That's a good one.
That's a good one. So thank you very much.
Thank you very much. And we have to find. Yeah, we have to find your car too. Ah, you recognize it's a green one.
Thank you very much.
Okay, thank you. You have to stop in front of the camera guy, in case. Okay, very good. Two teams are reminding now. One is from Ohio. They cannot make it, so they send also us. Their video to present themselves.
My name is Eric Masson. I'm a professor of chemistry at Ohio University. The interest of my research group is supramolecular chemistry. That means that we study how, why, and how tight molecules interact with one another. And because of that interest, we are going to be the engineers of a new nano vehicle that is going to be used or driven during the second Nanocar race in 2022. The first race took place in Toulouse in 2017, where the Ohio team, so me and Professor Hla from physics and astronomy, designed and drove the first prototype. And now we are coming with a new prototype for a new race.
This is Surface Science Lab. It's my lab. And basically this lab is designed for atomic manipulation. And we do have scanning tunneling microscope systems. Those are capable of moving individual atoms and molecules with atomically precise movement. We are not allowed to push the nanocar with a tip. We have to use either electron energy or electrical energy. So when we design the nanocar, we have included the charge locations. We call it the polar molecule. So the nanocar has the receptors which can accept the charge. So if we use the electric pulse from the STM tip, electrical pulses, depending on the polarity, the car will either move forward or backward.
So to power the car, we're going to need the tip of a scanning tunneling microscope, and this is what Professor Hla from physics is doing, so scanning tunneling microscopy. So he will drive the car using the tip of the microscope, and he's going to do it here while being in Toulouse remotely. The first design was, I would say, a nano wagon. So we had like a chassis, and we had 4 cucurbitryl wheels, so it looks like a car. And what we wanted to see in this new race is what would happen when you've got 2 axles instead of just 1. So we have the road, which is a gold surface. Then we would have here a first axle, and then on top of it, a second axle.
Gold has a special property. The gold 111 surface, we call it the herringbone reconstruction. Its atomic scale is a little bulky. So it's not entirely as smooth, it's just clean. Now the question is, some of the nanocars may not overcome those bumps. So we designed our car, a proper American car, bulky. We would drive through all these bumps. That's our plan. And we are going to win it.
I've got 2 graduate students right now working on the car. I'm also going to have most likely 2 undergraduate students working on the project, and very likely we are going to travel 2 graduate students to Toulouse.
This year we have 3 graduate students will be involved, and they are very important because they are the one who will prepare the sample. They are the one who are going to deposit the molecular cars, find the cars, to make everything ready. So they are going to prepare all these things. here locally.
They work from scratch, right? From just atoms that they connect together to make a molecule. And then from the molecule, they make the segue. And then from the segue, they deposit the segue on a surface. And then they drive the segue on the surface. So it's basically from the whole process from A to Z until the finish line. And of course, they learn some new science. They meet new colleagues. For example, students in chemistry are going to discuss science with students from physics. So it's basically this, cross-disciplinary aspect that's also very, very important.
Science without the public outreach is nothing. The science is funded by the taxpayer money. We need to inform the public what we are doing. Of course, we are not driving the nano car every day. We are working on our science. However, this is the great opportunity to reach out, to inform the public, hey, we can do little nano cars we can drive. And also we can make public not just aware, but also interested in it.
Also what was nice is to see young kids, right, coming to and talk with us and say, oh, this is really nice. Can you explain how that works? How cool chemistry or science is, right? At a young age is really important. I mean, this is really how our world works. But then there is really the fundamental aspect of what happens when you have molecules interacting with other molecules or molecules interacting with surfaces. How do they behave? Do they slide? Do they roll? How do they move? How do they proceed? Because in a sense, life itself is basically just a ballet between molecules that stick to one another. And that's why we're basically alive. So understanding how the whole process works, I think, is extremely important. So that's what we're trying to convey here.
So that was nice. I think we have succeeded to print the 3D model of Ohio. This is a real American car, almost 1 kilo of plastic, and almost 4 days of printing. Since we are in Toulouse, we can play rugby also with it, but take care, it's quite very heavy. So I don't know to who I offer it, or if I keep it, I don't know. So I keep it here, maybe. This molecule will move alone, we keep it here. We'll see at the end if this molecule is still there. So the last selected molecule is still there. Yes, you can. Okay, the last one, Patrick Caliputan, please.
Merci, Christian. Good evening, everyone. It's a pleasure to be back in this conference which awarded me a prize 3 years ago, and it's a pleasure to be back here in Toulouse, where I did my doctorate, actually. But this time, I'm not in the French or the Toulouse team. I'm in the Spanish team, which makes me feel like I'm a traitor. I'm betraying this city. But here we are, kidding aside. We are the Nanocar team coming from Santiago de Compostela and from San Sebastian in the northern part of Spain. So, yes. So, just a bit of introduction. For centuries, since the Middle Ages, people from all over Europe are going to Santiago de Compostela to do this Camino de Santiago, to do this pilgrimage. The journey could take them from 5 days to months just to end up in the fabled tomb of St. James. But this time, our car is coming from Santiago de Compostela, from the destination. It already arrived, actually. So it's synthesized there, and then it's being trained for racing in San Sebastian, a city in a region where the Camino also takes place. So that's one of our prototypes. The team is made up, this is the cathedral that they go to, the Camino, and then we have these two cities and the institutes from these two cities, SICUS and in the Universidad de Santiago de Compostela, and in San Sebastian in Centro de Física de Materiales, and we are sponsored by the Donostia International Physics Center. So the people who synthesized the molecule are led by Diego Peña, and for the theory, it's Nicolas Lorente and Roberto Robles. And for the LTSTM experiments, the pilots who are training the car for racing are me and yours truly and Tao Wang, and the other members of the team are Alejandro Berdonces, led by Martina Corso, and Dimas De Oteiza. So we are looking at different designs of the nanocar. These are our initial prototypes based on a coranoline moiety with a pyridine moiety in the middle to induce a dipole moment. They show these beautiful images, and we also look at what would happen if there's only one wheel. If it's a unicycle, we won't use it for the race. It's it's less than 100 atoms, but we look into these as well. We also look at twisted aromatics because they are already three-dimensional. They're easy to move on the surface, and they also show these beautiful assemblies. But in order to move them, we have to take them out of these assemblies, and they're working. We can move them by using the STM tip. We are currently making these cars faster and better to make them finish in 1 hour or 2 hours. And that's it. Thank you very much.
Wow, you're fast.
As fast as our nanocar.
That's okay.
Yeah.
I don't know if the Leo Grill team will agree about driving in 1 hour. I would not raise up the competition, but it's time to raise up the competition, guys. So let me see if we have, the last one. Here is the last one. I don't know if it's a real design. I don't know exactly what will be your design, but okay, you can, take care. Whoop. Keep this one here. If, thank you. If Professor So and Professor, I'll put it here because I don't have. So this is the conclusion of the presentation of the 8 teams which were selected for you and for all the people listening this streaming. In conclusion, here they are. You see, they are beautiful. We succeed to find different color, not exactly corresponding, sorry, for the team, for the color. It's not exactly the printing team. In random, we printed. So this is exactly with your sponsors you declare. Yeah, your sponsor you declare here, like Toyota, Air Liquide, and so on and so forth. And I just announce you that we decide after a lot of discussions that it will be in March 2022, the race. It will be normally broadcast direct on all the channels, and it will be the 3rd week of March up to now, depending, we don't know exactly which date it will be, but it will be for 24 hours. All the team will be in Toulouse and will drive via the internet connection, the STM everywhere in the world. It should be quite fun to have 8 STM driven from Toulouse for dispatching everywhere in the world. And finally, I'd like to thank all our sponsors, especially CNANO, Corinne, to allow us to present to you and to the people online listening this presentation, all the team which were selected among 23, the 8 which were selected. And I asked them to come, hey, with your car, come on. Hey, come on. Whoa, they are very slow, you know. Hey, 1, 2, 3, 4, 5, 6. And what I can do is I can take this one. Sorry, So and Eric online. I can take this one so you can be here all together. Go what you want. Like this, you have a finished photo all together. I'm here with this one. Good, good. So thank you very much and good luck to everybody. Hey, you have two. Yes. Okay. Thank you very much. And